Hello there, this is Thomas from investmentexcel.com. Welcome to this session where I will show you how to build a multiple linear regression model where we will try to estimate a relationship between a time series of stock returns and two exogenous variables of GDP, US GDP, and US 10-year Treasury bond. So it will be a estimation of a two-variable model in the technique with ordinary least squares. That is, we will minimize the sum of squared residuals between the observed price and the calibrated model price. We will also look at some statistics in addition to the essential feature of OLS, which is a fitting procedure. So the topic today is slightly advanced, and I would suggest you visit some of the other sessions I have made and which are available on investmentexcel.com on more simple topics regarding linear regression and also ordinary least squares estimation. Alright, this video of course is available as well on investmentexcel.com and perhaps also on spotify.com. Let's move on and take a look at the data. Okay, here I have an observation vector which can be set a little bit more simple, 25 observations of data. Here I have the stock price. Doesn't really matter which stock it is, it's just the stock price. And let's call it Y, which is what textbooks normally do when they label the endogenous variable in a regression model, also called the left-hand side variable. Here we have x1 and x2, the two explanatory variables in the model. First, the GDP. In interpretation-wise, when you use GDP in a framework of regression, we normally use the nominal amount in a period, particularly when we use it to forecast financial assets. So you could interpret this as US GDP for one period. And here is the price of a 10-year Treasury bond. So now what I want to do is to build a relationship, a linear relationship between the observed stock prices and the two explanatory variables. So the stock price, I assume, has a linear relationship to GDP and to the bond. I have no requirement, no restriction on the weights or on the parameters on the GDP and the bond. I just assume that the general function is linear. Indeed, we can use non-linear OLS as well, but please see other sessions on that. So, as I said, essentially the way to build the model is just by a fitting technique, ordinary least squares. So far we have said nothing about any statistics, and here is where many people they get a little bit wrong. OLS is a fitting technique, but based on the results you can assume some statistical properties, as we will see. But let's first try to fit the stock price with a model. And here I built the model. So I have a constant over here. Oops, sorry. I'll just put some other values in here because those are the correct ones that I calculated through the rehearsal. So first, the model is the constant beta 0 plus a multiplication between the parameter beta 1 for GDP. So this one times this one plus this one times this one over here. Up here we were. So this is the model. You can see if I do like this, the relationship here. I fix all these three parameters now, and these are variable vertically, and then I copy. No surprise they didn't change. So I'll just see if, yeah, okay. And now we have a residual, which is defined as the difference between the actual price and the model price. But in order to use the sum of squared residuals and the minimization technique in the OLS, we need to obviously square the residuals to avoid any netting between minus and plus differences. It doesn't change the optimization. So here we have the total sum of squared of residuals, and we'll try to minimize it by changing the parameters. I can do that in a couple of ways. I could use some matrix notation, but I will not do that here. I will rely on a solver technique, which we find in data solver. So I let Excel minimize this expression by changing the three parameters of the regression model, and solve. And it found a solution. And here you have the parameters. So now what I have done so far is to fit the actual prices of the stock with a model, and you see that here. The yellow line is the model, and the blue is the stock price. So if I just change this slightly, the model should be lower. This should be the optimal model in terms of minimizing the differences between the blue and the yellow. I'll just try to type 15 in and see if you get you see, quite sensitive. Okay, just solve again. So remember, regression is a fitting model, but if we apply some statistical intuition, we can work with the model in terms of statistical inference. Because right now I have no idea if this is a good model or a bad model. It might be the best in terms of the calibration, but if this historical data is supposed to be taken out of a population, in other words, if this constitutes a sample, because we want to use the model going forward with the information in history, so this constitutes a sample. Now it's just not observations, it's a sample, and the sample has to say something about the population, which is a philosophical expression for how we believe that the stock price in reality is linked to GDP and bond, not how it is given this one specific sample out of a billion samples. So we built a statistical model based on the linear relationship, which you see here, and the only thing we do is to add an error term, a noise, which we assume to be normally distributed with zero mean and constant variance. So this expression across all observations is the same, which means that the difference between the population value and the model, the right model, the true model, is normally distributed. And with this, we can take the expectations, because we want to create a model for the expected value. We know that there is statistical uncertainty, so we want to create a model for the expected value at every time. And obtaining this, we can always make a confidence interval, but we can never make a model for the exact population value. That's not possible, but we have an expectations with statistical uncertainty. This one we estimate, and I show that by taking the hats, and it can be shown with some algebraic manipulation that all parameters, they are what is called unbiased estimators of the true parameters. And with that in mind, we can assume that the real expected value is equal to the expected value of the estimation. And this is why we put the two equal to each other and make them make the difference as small as possible. In that way, the beta and the beta 0, beta 1 and beta 2 will be best possible estimates of the true population parameters. The last thing I just want to show you here is just to calculate the standard deviation that we so famously use in the statistical assumptions, the constant sigma. The OLS doesn't provide us with the sigma, so we have to calculate it manually, and the way to do that is first to remember what the standard error of the model is. And the standard error of the model is simply the sum of squared residuals adjusted for the number of observations and some degrees of freedom due to biasness in the estimated sigma versus the population sigma. So this is the standard error, and perhaps I missed just one thing here. It's actually the variance, so I just type in the square root, and now with this we can build our confidence interval for the predicted value of the stock price. So, for instance, you can take this one down here and make the interval. The model value, and make the interval around. You can have an idea or forecast of the GDP and bond 1 year ahead, calculate the predicted value of the stock price, the expected value of the stock price, and then you make the confidence interval. So the expected value of the real stock price in 1 year is given within, say, a 95% confidence interval, where you have the predicted value here plus minus the statistical uncertainty given by minus 1.96 times the standard error, and on the other side plus 1.96 times 42.3. So, and the reason why I just made it so fast was that I have a constraint on time at 15. So, that's it. Thank you very much.